So, I want to tell you a short story. Some of you may know it. Once upon a time, there was a farmer who lived in somewhere in a desolated village in southwest Virginia. And this farmer had a horse that he really loved, a beautiful horse. And one day, this horse became sick. And the farmer had to take it to the vet as soon as possible and earliest in the next morning. So the farmer gave it a bit of a thought and realized he doesn't know how to do it. Therefore, he summoned the three most senior scientists in his village and presented them with the problem. There was a mathematician, a physicist, and an engineer. So these three diligent scientists sat all day and all night with their laptops and whiteboards and models. And early in the morning, the farmer came with the horse and asked them, what should I do? So the mathematician said, look, I'm sorry, I couldn't solve it. And so did the engineer. But the physicist said, yeah, I have a solution. So the farmer asked him, great, what should I do then? So the physicist looks at the horse and said, I have a great solution for a spherical horse in vacuum, but this one is a bit more problematic. So I was so stressed about opening this conversation with the joke, which I usually tend to ruin, so I arranged the backup. Okay, so thank you. That's real. Okay, so spherical horse in vacuum is certainly not very valuable for a fast-moving company. But when I say spherical horse in vacuum, I don't only mean some vague abstract model which is not applicable, but also ground-to-earth, down-to-earth applicable model which cannot be delivered in time. But even the title of this talk is almost an oxymoron because research by its nature is uncertain. It requires many iterations and time, whereas fast-moving company requires fast results in a predefined tight schedule. So how do we as data scientists bridge this gap? That's the subject of the talk, and throughout this talk I'll use staffing for messaging as a case study to demonstrate these principles. So our experience is that we can do effective research in a fast-moving company, and the goal of this talk is to share tools and our experience how to achieve this goal. My name is Matan. I'm a data scientist at LivePerson. I have 20 years of experience as a research and algorithm developer. I worked in IBM research labs, in Runcom, BrightSource, and now in LivePerson. What's the agenda for the talk? First, I'll introduce LivePerson and tell you a bit about what we do and the staffing problem. Then I'll talk about scientific considerations and practical considerations. So, what do we do in LivePerson? LivePerson develops and provides platform for brands, for large companies, to communicate with their clients, with their consumers, via the various textual interfaces existing in the market today. For example, WhatsApp, Apple Business Chat, or just the web apps. So if I'm a large brand and I want to communicate with my clients, I can train agents and have them use LivePerson's platform in order to respond to customers. And if I'm a consumer of one of these brands, I can just open my mobile phone and click WhatsApp and click their IBM or Sky News or TMO and type the question, why is my balance so high this month? And after a few minutes, hopefully I'll get a response from the agent. So how does this look like when we are conducting a messaging-based conversation? It's just like a regular WhatsApp conversation. I know you don't see the text here, but basically there's the conversation begins with maybe an agent message issued at 12:31, and then the customer may respond after a while and asking some questions and so forth. Notice the times here. The conversation is asynchronous, so it may take, like the consumer may go to lunch and then enter a meeting, and then after 2 hours reply to the agent, which will respond again in its turn. Now, LivePerson does not only provide the messaging-based platform, but also a comprehensive suite of AI-based enhancement to improve both the brand's experience and efficiency and the consumer's experience. These include, among the rest, real-time reporting, intent analysis, sentiment analysis, sophisticated AI-based routing, and more. Today I'm going to use a particular component of this AI suite as a demonstration, as a case study. which is the staffing problem. What is the staffing problem or the staffing challenge? Suppose I'm a brand, I'm a company operating a contact center, a messaging-based contact center, and I want to achieve certain target service level. For example, I want my clients, my consumers, not to wait longer than 5 minutes in queue before they get the first response from the agent. So there arises the question, how many agents do I need to staff in the shift so as to achieve this target service level, which is the staffing problem. Why is it important? Here's just a thumb number. In the UK in 2019, 80% out of all the brand's revenues were dedicated to agent-related costs. So it's a huge percentage of the operation, the contact center costs. What happens if staffing is improper? So let's distinguish between two cases. One is overstaffing, in which there are too many agents. So in fact, this incurs redundant costs. The brand could have achieved the same target level by using less agents. On the other hand, understaffing is the case in which there are not enough agents to meet the demand. Therefore, long queues and wait times are formed. Customers become unsatisfied. They may abandon or deflect to other channels or leave the brand altogether. When I say brand, I mean a company, a large company operating a contact center. So proper staffing is worth a lot of money and satisfied customer. Therefore, it is an important problem to solve. So it seems a bit strange because we know that contact centers have been there for many years now. So hasn't this problem already been solved? Yes, it has. Who knows who this guy is? Agner Erlang. He was a Danish engineer, and he worked in the Danish branch of Bell Labs in the beginning of the 20th century. And he was introduced the staffing problem. In fact, he was introduced the problem of how many operators are required so as to achieve a certain target level, a certain demand, sorry. And between 1909 and 1920, he published a series of papers that provided an initial solution to this problem, which is the staffing problem. These papers pioneered what is now known as queuing theory, which is an important branch of operational research. Now, queuing theory does not only apply to contact centers or to banks or to queues in bus stations, but also to emergency departments in hospitals, to traffic in the road, to CPU scheduling, to computer networks, and even to ionic channels and cells membrane. In fact, whenever demand is introduced to a limited capacity, to a limited supply, queuing theory applies. Let's have a look at Erlang's model. The following slides are somewhat technical. It's not essential to understand the details, the mathematical details for the sequel of the talk, so don't bother about it if some notions are not clear. So Erlang developed a basic queuing theory, or a basic queuing model, in which there is a arrival stream, a stream of arrivals or jobs or customers that arrive at the system at a certain rate lambda. On the other hand, there is a set of agents, n agents in these examples. Whenever a vacant agent, an agent that is available now, whenever a conversation arrives, it is handled by a vacant agent. If there's no vacant agent available, the jobs are queued up in a buffer which is managed FIFO-like. It takes a certain time to handle each job or each customer. So each of these customers are assumed to arrive with arrive with a certain demand of a job, a certain quantity of job, which is measured in units in time, in units of time. So the service time is assumed to be a random variable with, or the service times between all the customers are assumed IID random variables. So this was the basic queuing model, and then Erlang made some severe assumptions as follows. These assumptions enable to solve and to obtain some closed formulas. So the assumptions are that the inter-arrival times, the time between successive arrivals into the system, are not only IID. This means that the process is not only a renewal process, but they are exponentially distributed. Hence, the arrival process forms a Poisson process. He also assumed that the service times are exponential IIDs with the average 1 over mu. Assume that the agents are identical, and there is a certain condition of the offered load which should be smaller than 1. Under these assumptions, the system in fact is Markovian, and the number of customers, the number of jobs in the systems form a birth-death process. Erlang applied standard Markov analysis, and he was able to derive closed form formulas for the steady-state distribution of important KPIs. For example, the probability of an arbitrary arrival reaching the system to wait in queue. This is the famous Erlang C formula. The wait time distribution, and also the queue size. Later on, in later years, another component was introduced to the basic model, which refers to abandonment. We know that customers do not have infinite patience. When we wait in line too long, we simply hang up the phone. So this is modeled by another component. Abandonment is assumed exponential as well. So why can't we simply use the existing model in messaging contact center? Well, the model simply doesn't fit, and the main reason for that is the asynchronicity of the messaging contact center operations. So let's have a look at several examples. In general, messaging operation introduces various peculiarities which are not addressed in the classical model. Let's see some examples. Let's look at the agent timeline. The classical model assumes an agent can either be idle or occupied, in which case he handles, a certain job. So the state space of the agents is binary. It can either, here is idle, and then the conversation enters, so the agent works, and then again idle, and so forth. The average duration of an occupied period is 1/mu, which is the service time. So this is what is assumed in the classical model. Let's see how it works in messaging. So here again, we look at the timeline. The horizontal axis is the timeline. And we're looking at the realization of a single agent at a single hour. All these three parallel lines designate concurrent conversations that the agent works on. So in messaging, the agent works concurrently on several conversations and responds to all of them. So here's one conversation, second conversation, and third conversation. And this all duration may last for an hour, for example. Upward pointing green arrows designate agent's messages. So here the agent wrote something and hit enter. And downward pointing arrows indicate consumer messages. So here the agent responded to this conversation, and then he switched to this one, and so forth. Let's zoom in on one of these conversations. So here, the consumer initiated the conversation, the agent responded, then he moved to other conversation, and after half an hour or so forth, another sequence of message took place. So there arises the following questions. When exactly is the agent working, and when is the idle? And also, what is the average net handle time of a conversation? So what do I mean by net handle time? A conversation may reside in the system, may be assigned to an agent for 30 minutes, 2 hours, or 36 hours. But the actual time required by the agent to resolve this conversation may be 10 minutes altogether, and that's the net handle time. So all these things are very different from the classical model. Let's see another example, what we call silent abandonment. We spoke about abandonment previously when I presented the Erlang's model. Which actually models the fact that customers hanged up the phone. But in messaging, the situation is very different. Here's an example for that. The consumer, again, initiated the conversation, then the conversation was assigned to an agent, and the agent responds. These are the green arrows. Then nothing happens. There's no further communication in the conversation. Either of the following three explanations are valid. One option is that the consumer abandoned before the agent responds, which is equivalent to hanging up the phone. But in messaging, it's not even possible technically to close the window. So we don't know about it. Another option is that the consumer is temporarily away and will respond later on, in 2 or 3 hours from now. Yet another option is that actually the single response by the agent has resolved the issue raised by the client. For example, the consumer asked, what's my balance? And the agent wrote, it's $50, and that's it. And the consumer didn't bother writing, thank you. So it's not very clear which of the conversation have actually abandoned. Here's another example, conversation again initiated by the consumer, then assigned to an agent. Nothing happens, the agent writes nothing, and then transfers it to another agent. There are various explanations for this phenomenon, but anyhow, all these phenomena and many more exhibit severe deviation from the classical model. Therefore, it's not applicable for our problem. So in general, the operation in contact center, in a messaging-based contact center, is very different from the classical model. So let's summarize what we saw so far. LivePerson does messaging-based contact centers. We saw that staffing is a crucial success factor for companies operating contact centers. And we saw that the staffing problem for messaging isn't trivial. So let's shift perspective now from the problem and the brands to us as data scientists working in a company. So we work in a fast-moving company. There's a tight schedule to deliver. We are introduced to a cutting-edge problem with no existing out-of-the-box solution, and we need to provide solution fast. So the focus goes to us as data scientists now. How do we conduct ourselves in these circumstances? And our experience indicate that the approach should be twofold. So basically, there are two main pillars. One is more tactical, which tools out of the scientific toolbox we have should we use? And the other is more strategic. How should we practically conduct the research under these circumstances? Let's go to pillar one, scientific consideration. So we have many tools as scientists. We saw some of them. And the question is, which one should we use in order to provide results fast and meaningful results? I remind you, our aim is to avoid spherical horse in vacuum. We need to provide value, and we need to provide it in the predefined schedule. Again, we are introduced this complex problem, non-trivial problem. We need to provide solution fast. Can we simply push everything to some neural network? Well, we can try, but it doesn't seem like very promising. And we saw some explanation for that in previous talks, but I'll explain why in our case. So a small detour. I have an apple here. And in a minute, I'm going to throw it on my vest. And I want to predict how long will it take the apple to hit the floor. So it took some time, and this great man in the slide, Isaac Newton, provided us with an answer to this question many years ago. And what Newton discovered or developed was an analytical model for the motion. It's the law of motion, stating that the force applied on the apple equals the derivative of its momentum. Now, in the particular case of the apple, when I apply the second law, it takes the form minus mg. M is the mass and g is the free fall acceleration. So I can use this amazing analytical model, substitute the parameters, and get an excellent prediction. Suppose I hadn't known anything about Isaac Newton and the law of motion, but I still would have wanted to obtain a prediction for the duration, for the impact time. Could I still have achieved a good prediction? Well, certainly yes. I could have taken 1,000 apples, throw them from various heights, measure the impact time, plot it all on a scatter plot. This is the height, and this is the impact time, and then perform regression. And this red line is just a statistical version of the law of motion, which I can use to obtain excellent predictions. So it seems that the analytical model is redundant. I can still obtain good predictions using a statistical model. So let's look at a slightly different example. Can we, suppose we are looking now at the question of a planet revolving around its sun, and we want to ask questions, for example, what's the revolution duration? Again, Newton's analytical model applies. It just manifests a bit differently than previously. So we can use Newton's analytical model to produce a good prediction. Could we use the statistical models that we've constructed using the apples to solve the planet problem? Certainly not. Yeah, it's a different scope, and it's a more general manifestation, a more general case of the problem in which the analytical model applies, but the statistical model requires update. So what I'm trying to demonstrate in this example is an important strength of analytical model comparing to machine learning models, statistical models. Analytical model generalize within its validity scope, whereas the scope of validity of a statistical model depends on the data set used to train it. And this is a very important distinction. So how does this manifest in the staffing problem? when we construct the models, we are using data sets from our clients, from LivePerson clients, which are brands operating contact centers. And what we see is that since most of them don't know how to properly staff, many of them are chronically overstaffed. It means that they maintain too many agents. It means that the data sets are degenerate. We don't see queues, we don't see wait times, we have no abandonment. There are constantly low agent loads, and therefore we can't estimate customer patience, we can't estimate or model using statistics or statistical model how agents perform at high load. So basically what we saw is that ML is great, ML is strong, but it cannot solve everything by its own. And in fact, there's no necessity it should solve everything by its own. We have amazing other tools. We have simulation, and there's ML or statistical learning, and there's analytical models. So which approach should we undertake when introduce this problem that we need to provide a fast result to? Let's do a short comparison. This is a big table. Please ignore the content of the table. Let's just stay with the colors, okay? So this is a sort of comparison table. The columns here are the various tools, scientific tools. This is the analytical model, ML model, and simulation. And the rows here designate various characteristics of these approaches. So the strength of analytical model is its generality. Yeah, scope of validity it applies, and it doesn't matter whether I've never encountered a specific part of the state space. Whenever I encounter it, the analytical model applies. Another advantage is that it's fast in terms of computation. There's a formula, I substitute in the formula, there's no faster computation. On the other hand, it's usually not realistic. Yeah, reality is always more complex than the theoretical model. And in terms of flexibility, it's rigid. It may take years to augment or extend an existing analytical model. What about machine learning? So one strength of machine learning is that all we need is data and statistical learning. We don't need to develop an extremely deep understanding or complex analytical models. We simply use the data, statistical model, and we have results. And the infrastructure is abundant. What about simulation? The great strength of simulation is its flexibility. All it takes is a couple of lines of code, and I can implement models which are even not traceable analytically after hundreds of years of research. For example, sophisticated routing schemes and so forth. So it's very quick to implement, it's flexible. The scope of validity, we can locally arrange a large scope of validity, even though we cannot span the entire state space. Last item is explainability. We've met some mentioning of this. So ML model explainability may be problematic, whereas simulation and even analytical models are almost obvious. This is the code, this is what it does. So, which tool should we use? And of course, we are using all of them. In the staffing problem, we know we are using the analytical model as the basis to our solution. Then we simulate the core, its core, and then we are using machine learning strategies mainly to estimate or predict various parameters or input going into the model. For example, the service rate that we saw, it's not easy to discern because of the asynchronous nature. We have just sporadic messages, and we need to deduce what's the service rate, and also the abandonment. We're using NLP, NLU, the textual means by which we can distinguish between silent abandonment and actual abandonment and non-abandonment. And later we even aim towards having the simulation as a basis to feeding a more general ML model. So, rather than choosing one of these wonderful tools, the approach we found very efficient is to combine them into a hybrid solution, which may not be extremely elegant, but it is effective and will enable us to provide results fast. Let's summarize this first pillar. We saw that single tool cannot provide fast, valuable deliveries. Unless it does, so by all means use it, but usually it doesn't happen when there's a complex problem. Each tool has its strengths and weaknesses, and by combining them into a hybrid solution, we are able to mitigate their weaknesses and take advantage of their strengths. Let's go into the second pillar, which consists of practical consideration, more on the strategic level. My main point here is that efficiently turning research into product requires careful conduction. It's not trivial. And the goal of this last section is to share practical tools to improve research efficiency and avoid pitfalls. What we'll see now is how to strategically conduct the research, how to cooperate, and some technical aids. So the first problem we'll encounter is how to choose our initial model. This, regardless of the exact tool, whether we use simulation or ML or analytical model, we need to work with some initial model. And there's a question of how to choose it properly. Now, since we are tight in schedule and we don't want to waste our time on oversimplified models, obviously we would like to choose a model that accurately captures the details of a system. For example, in the staffing problem, we know that the agent works concurrently on several conversations, so we want to put that into the model. We know that abandonment may be complex, so we want to put that into the model, and so forth. Otherwise, the model doesn't capture the essence of our system. And I can almost guarantee that by following this guideline, you will very quickly reach here. That's me a few months ago. So please, do not follow this guideline. Do not initially use a model that accurately captures the details of your system. Why is that? Because unless your problem is very simple, it will require many parameters to estimate, each of which will introduce noise and uncertainty into your model. It will be difficult to debug, and it will be difficult to stabilize an initial baseline for gradual improvement. What I do sincerely recommend is to follow the following guideline. Use the simplest model that can provide some value. We can dub this research MVP. It means that our solution may not apply to a horse, it may apply to a rabbit initially, or a donkey, but it will still be valid and it will provide value for our company. And since it's simple, it will be fast to implement. For example, in the messaging problem, in the staffing for messaging problem, we use the almost ridiculously oversimplified Erlang C model. We know that it's oversimplified even for telephony. Still, under certain circumstances, we were able to obtain good predictions. How? We've reduced the validity scope. We've identified that overstaffed brands do not have queues accumulating. They don't have abandonment. Therefore, the Erlang C that assumes no abandonment can apply quite reasonably. Then we've iterated and augmented the model. There are some much more complex models, Erlang A for abandonment, Erlang ANG for return to the same agent, and so forth. We can always iterate and improve and increase the complexity of the model. So, research MVP, choose the simplest model that provides some value, possibly reduce the scope of validity, and then gradually increase the complexity of the model. Following this guideline, we provide some value quickly and gradually increase the validity scope and the accuracy of our solution. So we know how to choose the tools, the scientific tools we work with. We use the rich toolbox and combine into a hybrid solution. We know how to choose our initial model. So most certainly our path to success is paved in front of us and we can simply follow it gladly. No, we can't, because we don't have metrics. We must have metrics in order to measure our progress and realize how the various more complex models improve our performance, and also to establish a baseline. We found it quite important and helpful that the metrics themselves are meaningful and tangible for the brands. We can always use out-of-the-box metrics, L1, L2 norms, and so forth, but we found an important value by providing metrics that mean something. For example, here is the blue one is the actual staffing, the number of agents, and the red one is the one we've predicted. We want our metric to indicate what's the cost of adopting our prediction. Whereas, so that's the accumulated error, but when measuring time in queue error, for example, we want to account for the relativity of the metric. For example, 1 minute error when aiming towards 1 hour time in queue is very different from 1 minute error when aiming at 2 minutes. Filtering is important. Our model is limited. Its scope of validity is limited. Therefore, we don't measure the errors or the metrics over regions where we know we don't claim to predict well. How we conduct the research. Tests are very important, as we know, but when doing research, it's not trivial. It's not like implementing a certain feature and writing automatic tests. We may examine 10 different optional research directions. Only 9 of them will actually materialize. So we don't want to waste our time writing automatic tests. On the other hand, it's quite embarrassing to report an amazing result based on a bug. So the thumb rule here would be a write test upon maturations toward productization. What else? Who knows what this is? Tower of Babel. Cooperation and collaboration was quite an issue there. We found that working agile using sprints, also in the research phase, not only in the production phase, was very helpful, and also tight collaboration with the product. Research proposals were very valuable, enabling us to estimate our directions and get the peer feedbacks. And code sharing and reviews were also very helpful. I don't have time to specify. Let's summarize. So pillar 2, research production requires careful conduction. How to work? Choose the metric first, then start by research MVP. Then use ascending hierarchy of models, each of which produces and augments the value that we provide to our company. Cooperation, use sprints, sharing, agile, code reviews. In terms of conduction, tests are important in the right time, documents, code reviews, and so forth. Here we can improve our efficiency, and by adopting these guidelines, we can improve our efficiency and avoid pitfalls. Let's summarize everything. So, spherical horse in vacuum is not very valuable for brands, and we as data scientists need to provide value under a tight schedule and provide it good. We can move fast as data scientists, yet build products that provide significant value for the company. What we've seen, LivePerson does great data science and is moving fast. Staffing for messaging is an important example for that. Scientific considerations, we saw how to use a rich toolbox and build a hybrid solution. Practical considerations, start with the metrics, then implement the simplest model providing value, and then iterate. It is true that all these tools and advices are not a magic formula that will by which we can avoid any dead ends or being late. But our experience indicates that all these are very valuable and enable fast progress and providing value quickly to the company. You're most welcome to contact me. My name is Matan from LivePerson. Thank you very much.